In this video, I want to do some more complicated examples. And here we're using composition, but we're composing different trig functions. So the cosine and the inverse tangent are not going to cancel. There's no chance that they're going to cancel like we saw in the last video where sometimes they would if it was the right domain. So here you're going to have to really break it down and they can get quite complicated. And you're going to start inside to outside. So the first thing you need to do is I do need to work through this piece here. So what is the inverse tangent of 5/12? Now, one thing to remember for inverse tangent is that the values that we plug in can be anything between negative infinity to infinity. So the 5/12 is fine here. No issues there. The only thing is if I go back to my tangent table that I made, right? So here's my tangent table that I was using for my inverses. I don't see 5/12 anywhere. I don't have 5/12. It's not a common one that I know. So I have a little bit of work to do. And what we can do here is we actually can use triangles. So what happens is I'm looking for some angle, right? When you have an inverse, you're trying to find the angle. That's what we get 5/12. Well, remember that tangent is equal to opposite over adjacent, right? So in this case, my 5/12 here, that must be my opposite and that must be my adjacent as well. So what's happening here, if I set up my little picture, well, opposite of my theta would be the 5. And then adjacent to my theta would be the 12. And I can go ahead and complete my little triangle by using the Pythagorean theorem, right? A squared plus b squared equals c squared. So 5 squared plus 12 squared would equal to c squared. That's 25 plus 144. So I get 169. And then when I take the square root of both sides, I do get 13. Now, of course, it's plus or minus a square root, but because it's a triangle, we don't want the negative. So I can complete my triangle and make that as 13 here. So now I can go ahead and use this to actually complete my problem. And you may be saying, well, how, we haven't really done anything yet. And what I'm going to do is I'm just going to rewrite for a second. So here is my original problem. And what I've been calling this is just theta, right? So whatever that angle is, I don't know. So cosine of this theta is equal to what? And in this case, remember for cosine is always adjacent over hypotenuse. So in my little triangle here, my adjacent is 12 and my hypotenuse is 13. And actually we're done here. So you may be like, well, why are we done? We didn't even find the angle, but we didn't actually need to find the angle here, right? The answer, we do need so the angle was needed for the inside piece, but the overall answer just required the cosine of that angle. So as long as we can make the triangle, we actually can answer the question without having to find the exact angle. And that's what we did here. We kind of did a workaround. 5/12 is not a common value that I know for my inverse tangent function. If it was something that I was used to, then I could just plug it in right away and move on. But I don't know that one. So I used a little triangle and I'm just using theta to hold whatever that value would be. And I was able to complete the question by finding the cosine of that angle with my triangle. All right, let's try another one. So same question, we're going to find the exact value. Okay, so I'm looking for the cotangent of the inverse sine of -1/3. Okay, so one thing I want to note again, just to kind of go back to just my inverse function for a second here. My inverse sine function, I can plug in anything between -1 and 1, and I will get a result. So this is defined, -1/3 is between -1 and 1. So it is defined, and I don't have to worry about that piece per se here. Now, the other thing I'm going to notice here is, I do know a lot about the sine function. If I go to my table, I don't have -1/3 though, right? -1/3 is not one of those common answers that I'm used to. If this was, -1/2, then I know the inside value is just -pi/6 and I can move on. But I don't have anything common here. So if I don't know the angle, I'm going to have to go ahead and use that triangle piece again as well. So we're going to go ahead and do that. Now, this one's a little trickier though, because I have a negative. So if I have a negative, it's not going to be a standard right triangle in the first quadrant. It's going to be in a different quadrant here. So I have to kind of think about what's going on. And again, I'm just going to work with this sine piece first. I'm going to work inside to outside. Okay, so again, I'm going to just relabel this for a second. So I know that theta is equal to the inverse sine of -1/3. But we could also relate this to sine as well, right? So sine of theta is equal to -1/3. And again, looking back at my inverse functions here and what's going on, that theta has to be between -pi/2 and +pi/2. And that's just how it was defined, right? So it does have to be somewhere between here and here. So notice a few things. One, my sine value is negative, right? Remember, your sine is always the y value. So this must mean the y value is negative in the plane. And the theta has to be between -pi/2 and +pi/2. So it has to either be in the first quadrant, which is 0 to pi/2, right? Here's 0 pi/2. Or if I'm doing negative, then I'm going down this way. So it has to be in one of these two quadrants. Because of the way the theta is defined, but sine is negative and that's the y value. So it must be a negative y. So I don't know exactly what the angle is, but it's something like this, right? So it has to be somewhere over here, and it has to be going this way. So my theta then must be, this piece right here. So it's going to be some sort of, it's this negative angle here. Now, the other thing that we can think of as well as we're thinking about triangles here, because we're kind of making like a little triangle, is that we know that sine of theta is -1/3. And if I think about this in terms of triangles, well, again, sine we said relates to the y, so that would be the y over the radius here if I'm going to draw a triangle. Now, your radius cannot be negative, right? So it must be that, again, the y value is negative. So what I'm noticing here is that my y value is -1 then, and my radius must be 3. So I can use that idea that x squared plus y squared equals r squared, or we've also seen the formula r equals the square root of x squared plus y squared. So they both really work the same way. I'm going to use this version because it's just easier. I'm going to have to square everything anyway to simplify. So I would have x squared plus -1 squared is equal to 3 squared. X squared plus 1 equals 4. If I subtract 1 to both sides, I do see that x squared is equal to, this is 9, not 4. If I subtract 1 from both sides, I see x squared is equal to 8. And then when I take the square root there, x is equal to the square root of 8, positive because we're talking about triangles here. And also because if we're in the third quadrant, your x value is positive there. You can see that too. And I get 2√2. All right, so this first part is done. Again, we're using the idea of triangles. Here it's a little bit different. So this is the section on any angle because everything is not positive here. So we're in the third quadrant and you have that y value that's negative, but it's sort of the same idea. You're still kind of using this idea of a radius and applying that Pythagorean theorem. So again, still very, very similar process as you go through. So now I have my pieces set up here and I can finish this. And again, I don't really actually know what the theta is. So keep in mind, I actually haven't figured out the theta, but I don't need it because I can still find the cotangent of that theta using all my x, y, and r pieces, using my triangle pieces really. So I'm just going to relabel that inverse sine of -1/3. I'm just going to call theta just to hold that place. So I'm looking for cotangent of theta. And if you think about the formula there, talked about it, it was the x over the y value, right? Because tangent is y over x, so the opposite of that. And I know my x value now is 2√2. I know my y value is -1. So my answer here is -2. Okay, so I have the problem written out for us. And it says if 0 is less than x is less than or equal to 1, write cosine of the inverse sine of x as an algebraic expression in x. Now you're probably saying, well, there's already an x there, but they really sort of want us to rewrite it more so without the inverse functions and the trig functions and things like that. So we want to clean this up as much as possible. So again, I'm going to use this idea where I don't really know the answer. So I'm just going to call the answer theta, because we know when you're finding inverse functions, you're finding the angle. So I'm just going to call it theta. But you can also rewrite this, right? So it's the same thing as saying that sine theta is equal to x. These two are interchangeable, which is how we defined the inverse function to begin with, right? Just bringing back some old notes here. That's how we defined it. And do remember as well that we were restricting the domain there between -π/2 and +π/2 as well. So one thing to think about a little bit is you want to think about where we are in the domain, or in the unit circle, really more so than that. Two examples, we saw that we were in the first quadrant, so we were able to just kind of draw a quick triangle. In the last example, we were in the third quadrant, so we did more of a unit circle picture there to help us find the x, y, and r. Here, if we think about this, a couple things. One, I do know that my angle is between -π/2 and +π/2, right? So that's -90 degrees and +90 degrees. So I'm either in the first or fourth quadrant. I have to be on the right side of that unit circle, either going up to 90 or down to -90 degrees. So I'm on the right side of the circle. I also know that, again, my x is between 0 and 1 here. So that also is helpful, that my x value is between 0 and 1 here. And we also know, because of that, that sine is positive, right? So if x is between 0 and 1, then sine of the angle has to be positive. And sine represents the y value. So if the y value is positive, it must be up here, up top of the graph. So we must be in the first quadrant in this case. And again, these are tricky. They take a lot of thinking through. You really want to think about where are you on the unit circle. In this case, we have to be in the first quadrant because one, sine is positive because your x is greater than 0 and less than or equal to 1. And our angle also has to be between -π/2 and +π/2. So when we put those two things together, you have to be in the first quadrant. So we can draw just a regular triangle here. Or if you want to draw a unit circle picture, you can do that too. So we're somewhere here in that first quadrant. So maybe we look like this. Now I'm going to use the unit circle here. So my radius is going to be 1. And then I do need to do a little bit of work here. And this is going to be, let me draw this a little bigger actually. Draw my triangle a little bit larger here. So this is going to be my theta. My radius is going to be 1. And then what's going to happen is if you think about sine, right? So sine of theta is opposite over hypotenuse. And the sine of theta was x here, right? So it's x. And I know my hypotenuse is 1. So opposite is going to be x, and this is going to be 1. So I can use my Pythagorean theorem here. And we can just call this y. So x squared plus y squared is equal to my radius, which is 1 squared. And if I do a little bit of work here, I'm solving and I see that I have x squared plus y squared equals 1. If I subtract the x squared to the other side, y squared equals 1 minus x squared. And then I can go ahead and take plus or minus the square root. But again, really, I'm just looking for the positive square root here of the other side of the triangle. So this bottom side of the triangle is 1 minus the square root of 1 minus x squared here. So cosine of inverse sine of x, again, I don't really know what this is. I'm just calling this theta. So we're doing cosine of theta, and I'm going to use my triangle here. So we have our theta in there as our placeholder, because again, we're not actually going to find the exact angle here. We're going to use our setup of our triangle, but just use that theta as our placeholder. And now you want to remember that cosine is always the adjacent side over the hypotenuse. So in this case, if I look at my theta, where the position is, my adjacent side is this y value. It's the square root of 1 minus x squared. And then my hypotenuse in this case is just 1. And of course, I can simplify that to 1 minus x squared. So this is the answer we're looking for here. This is what they mean when they want an algebraic expression in terms of x. So we're kind of removing that cosine and sine from the piece here. We're simplifying that as much as possible. So when you're composing two functions that are trig functions and things don't cancel out easily, right? So they're not perfect inverses, or we're not in the right domain or something. The best thing to do is to either try to use triangles if you're in the first quadrant, or if you're not in the first quadrant, you can go ahead and use a similar style. You're still using that x, y, and r idea, but in one of the other quadrants. And you just want to be careful and think about the signs then if you're not in the first quadrant, because you do have a negative in there somewhere. So for these ones, take your time. Draw your pictures, really think through as to what quadrant you're working in. And then once you have your setup, we're able to use the Pythagorean theorem to find any remaining sides. And our basic formulas for sine, cosine, and tangent with that triangle afterwards.